Hello everyone and welcome to the second part of our 31st lecture of today, the 24th day of April in the year 2020. So, we are now going to talk about line integrals of vector fields. In part 1 we talked about line integrals of scalar valued functions. Now we're going to discuss line integrals of vector fields. So we're still going to be integrating along smooth curves. All the discussion that we had of smooth curves still applies, but now our integrands will be vector fields instead of scalar valued functions. So the primary theorem for this topic is given here, line integrals of vector fields. You've got a curve C with a given parameterization and it is smooth. And we have a vector field from R2 to R2, so a vector field on the plane, excuse me, which is continuous along the curve C. Then this is the expression that we use to indicate the line integral of f hat along C. And you'll notice that it's different. We're taking f hat and we're dotting it to what we're saying is dr. So you can think of this dr expression as being the tangent vector along the curve. R hat gives position and dr is going to be something like the tangent vector, r hat prime. And in fact, we're going to talk more about the intuition and why this symbol is the way that it is in just a moment. But in fact, to compute such an integral, this is what we would use to refer to the line integral of this vector field f hat along this smooth curve C. And to compute it, we use this formula. So our integral is again from a to b, where just as before, backing up a slide, a and b are the bounds on our parameter for this parameterization of this smooth curve. We're integrating from a to b. We've got the vector field taken along the curve, and we're taking a dot product between the vector field and the tangent vector. And this integral is with respect to t. So the dot product is also known as the scalar product, if you recall, and it returns a scalar value. So this is actually just a scalar valued function here of t, this whole dot product is. And so it makes sense that I can take a Calc 2 style integral of that expression with respect to t. So for the intuition, Stewart doesn't actually do as great of a job here. There's a nice picture on page 1125. That's actually the exercise section of the book. If you have a look at problem 18, there is a nice picture where I have adapted here somewhat. So you can have a look at a better drawing, but the gist of the issue is here. So in blue, we have our vector field. Every point in the plane has a vector associated with it, and those are shown in blue. In red here, I've given you a smooth curve C. And so in our calculation of the line integral of this vector field along this curve, we have this dot product. So let's think about that dot product right here. The dot product, if you remember from way back when we were working on chapter 12 material, or even chapter 11, I can't remember exactly where dot products come up, but in the beginning of this course, we talked about dot product, and we realized that with the cosine of theta expression involved in the dot product is always positive and maximized when the two vectors in question align with each other, when they point in the same direction or in roughly the same direction. The dot product is famously 0 when the two vectors are perpendicular, and the dot product will be negative if the two vectors actually point in the opposite direction. So looking here at my curve, r hat prime is always the tangent vector to my curve. So in this portion of the curve here, it looks like my tangent vector, which points in the direction of motion along the curve, indicated by these red arrows, but my tangent vector is going to correspond pretty well with the direction of the vector field. So that dot product is going to be positive in this portion of the curve, and we will be contributing positive values. Remember that integrals are always sums, so we're summing up a bunch of different values of all these dot products, and along this region of the curve, those dot products are positive. Once we get around here somewhere, it's looking like the vector field will be perpendicular to the tangent vector, and so that dot product will be 0. And then as we make this turn and head back in towards the origin, our tangent vector is actually pointing in the opposite direction of the vector field. And so the dot product that is our integrand here is going to be negative in that portion of the curve. So we can get some sense of what this integral means by thinking about the integrand and thinking about when it is positive, when it is 0, and when it is negative. And in fact, the integrand is positive whenever our tangent vector for our curve, r hat prime, aligns well with the vector field. And our integrand is 0 when these two vectors are perpendicular, and it's negative when they point in opposite directions, as they do along this final portion of the curve here. So really what we're seeing is sort of the cumulative total of the degree of correspondence between the tangent vector and the vector field. There'll be portions, if the total integral here is positive, then that means more often than not our tangent vector corresponded with the vector field. And I'm speaking roughly. It also depends on the magnitude of both of those vectors, but speaking roughly, there is greater weight assigned to the region where the tangent vector and the vector field corresponded. If this whole vector turns out to be negative, then for the most part, the tangent vector and the vector field were at odds with each other, pointing in opposite directions or nearly opposite directions. A good intuitive way to think about it is if I let my vector field be a wind pattern, right? So I'm seeing the direction and the intensity in which the wind is blowing at different points. To what degree would that wind tend to push a bead along this string? If I let my curve be a string, to what degree would the wind tend to push the bead along the string in the indicated direction? And again, there'll be regions where the wind is pushing the bead along the string in the positive direction, and there'll be regions where the wind is attempting to push the bead back along the string, and those correspond to negative values. And so it gives you some sense of that. Hopefully that makes some sense. So this is the idea of a line integral of a vector field along a smooth curve C. So, warning, these two formulas that we are studying in part 1 and part 2 of today's lecture are very similar. So here they both are. We can integrate scalar valued functions little f along curves with respect to arc length. We can integrate vector fields along a curve C with respect to this dr expression here. And when we integrate scalar valued functions, we're getting little f at r, and we're multiplying that by the magnitude of r hat prime. When we integrate vector fields, we're getting big F at r, and we're dotting that to r hat prime itself. So in both of these, you're taking your integrand along the curve. It's little f or big F at r hat prime. When little f is scalar valued, we have to multiply it by another scalar valued function, which is why we take the magnitude of the tangent vector. When big F is a vector itself, we can dot it with another vector, and so we take the dot product with the tangent vector itself. Both of these involve something like multiplying by the tangent vector, but it's either actually multiplying by its magnitude or taking the dot product with the tangent vector itself in these two different scenarios. And so the fair degree of similarity between these two formulas is why I am encouraging you to be extra careful when you are deciding which of them is relevant to the problem at hand. You really need to think about your integrand. Is it scalar valued or is it a vector field? What kind of outputs does it generate? Does it output numbers or does it output vectors? And that's going to decide which of these two formulas you need to use. So let's look at an example and a sample problem for some line integrals of some vector fields across smooth curves. So here is a vector field. Big F hat is given by this vector where the first component is x times y squared and the second component is the opposite of x squared. Let's integrate that along the curve given by parameterization t cubed comma t squared, where t is going between 0 and 1. So the first thing I'm going to do, and again I recognize that we're operating under the heading of line integrals of vector fields, so it's probably fairly obvious that this is going to use the theorem that is relevant to line integrals over vector fields, line integrals of vector fields over smooth curves. But in general, on tests and out in the world, nobody has to tell you that ahead of time. So the first thing you should always do is think about your integrand. If you're thinking about line integrals, is your integrand a vector field or is your integrand scalar valued? This integrand outputs vectors. If I back up and I look at it, if you feed it an xy pair, it's going to spit out a vector, right? If I feed it 1, 1, it gives me 1, -1, the vector. And so this is a vector field. That means I'm going to use the formula which is relevant for vector fields, shown here, the one we're discussing in this part of today's lecture. So we need to find all of this stuff inside to be able to put it all together. We need f hat of r hat, we need r hat prime, and finally we need the dot product of those two vectors, and that will become our integrand. So I'm going to find those things in turn. F hat of r hat. So f hat looks like this, that was given in the problem. R hat looks like this, which is given in the problem. That means that along curve C, my x values are always t cubed, and my y values are always t squared, and I've written that here. When I'm talking about f hat of r hat, I want the values of f, my vector field, along the curve C, given by r hat. Let me back up for a moment here. I generally don't care what the vector field is doing over here. I only care what the vector field is doing along the curve. That's why I'm looking at f hat of r hat. So along this curve, x looks like t cubed and y looks like t squared. So my f hat of r hat is going to have this x y squared. Is that right? Yeah. X y squared, and then the opposite of x squared here. X is t cubed, y is t squared. And I simplify that and I have this expression for f hat. I can find r hat prime. Derivatives of vector valued functions are just taken component wise. That's not difficult. And I find it here. And now I can dot these two vectors. So the dot product of f hat along C together with the tangent vector along C is going to be the dot product of the two vectors I just found, and it turns out to be this polynomial, an unusually large order polynomial for a calculus class, but a polynomial nonetheless. And now I just integrate it. So the integral of this vector field along this smooth curve is given by this expression, where this got away from me a little bit, but that is an r hat prime of t there. And the limits of integration are the bounds on our parameter, which were given as 0 and 1 for this t. I can substitute in the expression I found for that dot product, and I'm just taking a Calc 2 style integral of a polynomial here. So we're getting this expression, plugging in values, and I'm actually solving numerically because it was particularly easy for this one. So the answer is 1 over 20, or 0.05. We are seeing a positive value, so that does mean that in general the tangent vector for this curve lined up with the vector field more often than not, in some sense. Again, that's a slight oversimplification because you also have to take into account the magnitude of the vectors. If the tangent vector only lines up with the vector field in a small portion of the curve, but the vector field is large enough in magnitude over that small portion, you could still see a positive value there. There is a weightedness to that sum. But speaking in a somewhat informal way, taking the integral of a vector field over a smooth curve is a measure, in some sense, of the degree to which the vector field lines up with the tangent vector to that curve. And here we found it to be positive at 0.05, 1 over 20. All right, let's have you folks try one of these. So here's a new vector field given in the I hat j hat notation. And here is a curve, which I also meant to give in the I hat j hat notation, but I forgot and defaulted to the bracket notation, which I tend to prefer. That's okay. Go ahead and find for me the line integral of this vector field along this smooth curve. Alright, that should have been ample time to pause the video, so let's have a look at this. We have a vector field. The first thing I'm going to do is double check that my integrand, whether it is a vector field or a scalar valued function, and this is a vector field. So we can compute the line integral of this vector field along this smooth curve using the theorem that we are considering in this second part of today's lecture. Here's my vector field where I'm doing away with the I hat j hat notation and writing it back in terms of brackets, and here's my r hat. And I've got my bounds on my parameter that will ultimately become my limits of integration. I can take f hat at r hat. So the first component of f hat is e to the x minus 1, but along curve C, x is t squared. So I get e to the t squared minus 1. And then the second component of my vector field is x times y. Here's x and here's y. If I multiply those two together, I get t to the fifth. So this is f at r hat. This is the value of my vector field along the curve C given in terms of parameter t. And I can find the derivative of r hat easily enough. It's going to be 2t and 3t squared as the components. And I can take the dot product of these two. I'm going to get the product of the first components, 2t e to the t squared minus 1, and the product of the second components, which will give me 3t to the 7, multiplying like bases and adding the exponents there. So now I have my dot product. And now it's all over but the Calc 2 style integral that must be computed. So the integral of this vector field along this smooth curve is given by the integral from 0 to 1 of the dot product of the values of the vector field along the curve together with the tangent vector. Again, this is the core concept here, that we're looking at what degree does the vector field correspond to the tangent vector. And we're finding that correspondence via dot product. So I already found that analytically, and here's the expression. I'm going to break this up into two integrals with respect to t, because this one is a straightforward polynomial, whereas this one requires a u substitution. U here is t squared minus 1. I haven't bothered to write in the u schema, but I am taking u to be 2t rather. U is t squared minus 1, so that 2t dt is my du expression. And that integral simplifies to just e to the t squared minus 1. You can always double check by differentiating these expressions and making sure you get back your integrand. And again, if you want to work out the details of that u sub, if it's not obvious, I encourage you to do so. Hopefully you already did it. This was a sample problem, so hopefully you already saw that. And then we've got our 3 over 8 t to the 8th here. We're going from 0 to 1 for these t values. Plugging in 1, I get this expression. We're looking at an e to the 0, which is 1 and 3/8, and then minus the value at 0, which is going to give me e to the negative 1 and a 0. So 8 over 8 plus 3 over 8 is 11 over 8 minus e to the negative 1. And this again turns out to be positive. E is greater than 1, so 1 over e is less than 1, and I've got something larger than 1, and I'm subtracting off something that's less than 1, so it turns out to be positive again here. It's just a point of interest. Alright, I appreciate that, folks. It's looking like we will be doing this next time, where we will take the first little portion of next lecture, and I will throw probably roughly 4 line integrals at you, and will not tell you which type of line integral it is, and you'll get some more practice performing these line integrals, and better still, you'll get practice deciding which type of line integral is it. Is it a line integral of a scalar valued function or of a vector valued function? If it seems like a simple distinction, that's excellent. I have taught the class often enough that I have seen that students will struggle with that initially, so I definitely want us to have a bit of practice in the first part of next lecture before you encounter such problems on an exam. Alright, I thank you, folks. I hope you have a lovely weekend, and I will speak with you again on Tuesday.